Now I'll discuss spherical mirror and its types. Now what is a spherical mirror? A mirror which is made from a part of a hollow sphere. Those mirrors are called spherical mirror. All of you know what is a sphere. This type of objects, cricket ball, football, they are called spheres. So from a part of this type of spherical object, if we can prepare one mirror, then those mirrors are called spherical mirrors. Spherical mirrors may be concave or convex. Now what is a concave mirror? Mirror which is polished from the outer side of a hollow sphere such that the reflecting surface is towards the hollow side. Suppose if I consider this spoon, in this case, if this part we consider the mirror, that means this is the reflecting surface, then this type of mirrors are termed as concave mirror. And what is a convex mirror? Convex mirrors are those mirrors which are polished from the hollow side of the sphere such that the reflecting surface is towards the bulging side. That means if this is the reflecting surface, then those type of mirrors are called convex mirror. Now while drawing, we draw like this. This is one concave mirror, this is one convex mirror. Now after drawing this type of mirror, you have to imagine the whole sphere. So while drawing, it appears to be a circle. Then whatever is the center, this center and the middle point of the mirror, which is also known as pole, if I join, then we are going to get one imaginary line. Those imaginary lines are called principal axis. Here I have drawn one convex mirror. In case of this convex mirror also, if I imagine this to be a circle, then there will be a center. This center and the midpoint of the mirror is also known as pole. If I join by an imaginary line, this line is called the principal axis of the mirror. So in case of convex mirror, this is the principal axis, and in case of concave mirror, this is the principal axis. Now let me discuss some general terms associated with spherical mirrors. First, pole. What do you mean by pole of a spherical mirror? It is the midpoint of a spherical mirror. Suppose this is the mirror, then this point is called the pole of the mirror. Second term is center of curvature. Center of the hollow sphere of which mirror is a part. So this is the mirror, and assume that this is the hollow sphere. Then there will be a center. This point C is called the center of curvature. Third term is the principal axis. It is the imaginary line passing through the pole and center of curvature. So this point is the pole and this is the center of the imaginary sphere. If I join this C and P by an imaginary line, because whenever we see this type of mirrors, we cannot see this type of line. So that's why it is written imaginary line passing through the pole and center of curvature. Those lines are called principal axis. Clear? Next term is a linear aperture. Linear aperture means, suppose this is the mirror. Distance between M and N, linear distance between M and N is called the linear aperture. Definition wise, we say it is the diameter of a spherical mirror is called the linear aperture. In this case, Mn is the linear aperture. Next one is the principal focus. Principal focus, it is a point on principal axis where a parallel beam of light after reflection either actually or appears to meet. Here you can see, here I have drawn one concave mirror. These are two rays which are parallel to the principal axis. Already you know this one is the principal axis. This ray and this ray, these two rays are parallel to the principal axis. These rays, after reflection from the mirror, they meet at a point in the principal axis. The point where these reflected rays meet, that point is called the principal focus. Generally we represent this point by F. Now in case of a convex mirror, the principal focus is behind it, whereas in case of a concave mirror, principal focus is in front of it. Clear? Now the linear distance between pole and the focus. The linear distance between pole and the principal focus, this length is called the focal length. That means starting from P up to F, this length is focal length. In this case, distance between P and F, this length is called the focal length, and it is generally represented by the symbol small letter f. And now the next term is radius of curvature. The linear distance between the pole and the center of curvature of a spherical mirror is called radius of curvature, which is represented by the symbol capital letter R. So here CP, this distance is called radius of curvature. Here it is C to P. That means the distance between center of curvature and the pole of the mirror. Okay, and what is focal plane? It is an imaginary plane passing through principal focus such that it is at right angles to principal axis. So here you can see this is the principal focus, here this is the principal focus. Now if I imagine one plane which is perpendicular to the principal axis and passing through principal focus, those planes are called focal plane. Suppose this is the plane which passes through F and is perpendicular to the principal axis. This type of planes are called focal plane. The radius of curvature is twice of focal length. Let me prove it. Suppose this is one concave mirror, this is principal focus, this is center of curvature, this is pole, and AB be any ray which is parallel to the principal axis. This ray after striking the mirror will reflect and it will pass through the principal focus and it will go this way. We have joined B and C. Now we know angle of incidence equal to angle of reflection, therefore angle I equal to angle R. This angle we have named angle 1. Now since AB is parallel to CP, angle I and angle 1, these two angles will be equal because they are alternate interior angles. I think you know that if these two lines are parallel and one transversal is there, then these two angles are equal. Then these angles are called alternate interior angles. So here angle I and angle 1 will be equal. So previously we got angle I equal to angle R. Again we got angle 1 equal to angle I. So from these two relations we can write angle R equal to angle 1. Angle R equal to angle 1. Now we know in a triangle, if these two angles are equal, their opposite sides are equal. Similarly here, angle 1 and angle R, these two angles are equal. Therefore CF equals to FB. So we got in triangle CBF, angle R equal to angle 1. So FC equal to FB, sides opposite to equal angles. Since the mirror is a very small aperture, we can consider FB equal to FP. Previously we got FB equal to FC and now we got FB equal to FP. So from these two we got CF equal to FP. Therefore F is the midpoint of CP. Now radius of curvature, that is written as capital R, is equal to CP. Now CP can be written as CF plus FP, CF plus FP. CF and FP both are equal, so we can write FP plus FP. So twice FP, and FP is nothing but focal length, so we can write twice of F. That means R equals to twice of F, or F equals to R by 2. That means focal length is half of radius of curvature. Now let me discuss the rules for drawing images in case of a concave mirror. Now this is a concave mirror, this is the principal axis, this is C, center of curvature, F is the focus, and P is the pole of the mirror. Now any ray of light which is traveling parallel to the principal axis, this is the principal axis, and if the ray is parallel to the principal axis, after reflection always the ray will pass to the focus of the mirror. This is rule number 1, that any ray which is traveling parallel to the principal axis, after reflection from the mirror will pass to the focus. This is rule number 1. Now we can say any ray of light which passes through the focus, any ray of light which passes through the focus of a spherical mirror after reflection travels parallel to the principal axis. It is just the opposite of this one. When the ray is parallel, it will pass to the focus, and when the rays pass to the focus, they will become parallel to the principal axis. Now rule number 3 is that any ray of light which passes through C, means center of curvature, after reflection will retrace its path. It is because this line is the normal. If I imagine here one plane mirror, then this will be the normal. So just like normal incidence, this ray of light will retrace its path and it will just move in the opposite direction. And rule number 4 is that a ray of light incident obliquely to the principal axis towards the pole is reflected in such a way that angle of incidence and angle of reflection with the principal axis remain same. So any ray of light which strikes the pole, it will reflect in such a way that angle formed with the principal axis will be same as angle formed by the reflected ray with the principal axis. So these are the 4 rules that we have to remember while drawing images in case of a concave mirror. So let me just revise. When a ray of light is parallel to the principal axis, after reflection it passes through the focus. A ray of light which passes through the focus, after reflection it will become parallel to the principal axis. Any ray of light which passes through C means center of curvature. After reflection will retrace its path, that means it will rebound in the opposite direction. And a ray of light which strikes the pole will reflect in such a way angle formed by the incident ray with the principal axis and the angle formed by the reflected ray with the principal axis remains same. So these are the 4 rules that we have to keep in mind while drawing image formation in case of a concave mirror. Let me now discuss the formation of image in a concave mirror for different positions of the object. In case 1, now we are considering when the object is at infinity and the rays coming from it are parallel to the principal axis. The rays coming from an object at infinity are always parallel. So here, since the object is at infinity, so rays which are coming from that object must be parallel. Here we have considered this ray which is parallel to the principal axis. And already I told you, any ray which is parallel to the principal axis, after reflection from the mirror always passes to the focus. So this ray will pass to the focus. This is another ray which is parallel to the principal axis, and after reflection from the mirror, this ray also will pass through the focus. These 2 reflected rays are passing through this point F. So the image that will be formed in case of a concave mirror when object is at infinity and the rays coming from it are parallel to the principal axis, the image will be real because rays are really meeting. Real images are always inverted, that means the image is inverted, and as you can see, only a small dot image is of very small size, so we write highly diminished and the image will form at F. So these are the characteristics of the image formed by a concave mirror when object is at infinity and the rays coming from it are parallel to the principal axis. This is the second case when object is at infinity but the rays coming from it are not parallel to the principal axis. Now these parallel rays after striking the mirror will reflect and they will meet in the focal plane. So image will be somewhere in the focal plane. Just like the previous case, here also image will be real because the reflected rays are meeting at a point. That's why image is real. Real images are always inverted, and as you can see, this small dot is the image. So it is highly diminished and the image will be in the focal plane. So these are the characteristics of the image formed by a concave mirror when object is at infinity but the rays coming from it are parallel but not parallel to the principal axis. Now in case 3, object is beyond C and this is the object. From here we have to draw 2 rays for the formation of image. Suppose this ray which is parallel to the principal axis, after deflection from the mirror, this ray passes through the focus. We know any ray which is parallel to the principal axis after reflection from the mirror always passes to the focus. So this ray after reflection will pass through the focus. Any ray which passes through C, it will rebound. That means any ray which passes through C, it retraces its path. So this ray after reflection from the mirror will move in the opposite direction. So this is one reflected ray and this is another reflected ray. So this reflected ray and this reflected ray are meeting here. So if this is the object, then this will be the image, and here you can see the image is smaller than the object. Image is smaller than the object and the rays are really meeting. So image is real because the rays really meet at a point. Real images are always inverted, and here you can see object and this is the image. So this is inverted. So image is real, inverted, and as the size of the image is smaller than the object, that's why image is diminished and image is formed between C and F. Now case 4, when object is at C. C means center of curvature. Here this is the object. We know from the object many rays are moving in different direction, but for the image formation we have to draw 2 rays. This is one ray which is parallel to the principal axis. always it is better to draw a ray which is parallel to the principal axis, then image formation becomes easier. So we know the rule that any ray which is parallel to the principal axis, after reflection from the mirror passes to the focus. So this ray, whatever is coming from this point, after deflection from the mirror, this ray passes to the focus. This is another ray which passes to the focus, and any ray which passes to the focus after deflection from the concave mirror, it becomes parallel to the principal axis. So this is one reflected ray, this is another reflected ray. These reflected rays are meeting at this point. So if this is the object, this will be the image. If this is the object, this will be the image. And as you can see, here rays are really emitting, so image is real. It is inverted, and the height of the object is same as height of the image. So the size of the image is same, and it will form at C. So we can say when object is at center of curvature, in case of a concave mirror, image that will be formed, it will be real, it will be inverted, and it will be same size, and always it will form at center of curvature. This is the fifth case. When object is between C and F, you will find that one ray which is parallel to the principal axis. After reflection from the mirror, this ray passes through the focus. Another ray which passes to the focus, after deflection from the mirror, it will become parallel to the principal axis. So this is one reflected ray, this is another reflected ray. These two reflected rays are meeting here. So this will be the image. This is the object, this is the image. And as you can see here, the rays are really meeting. That means image is real. Real images are always inverted, and here you can see the object is this one is the image, so image is inverted. Height of the object is smaller and height of the image is bigger. That means the image is enlarged. Whenever height of the image is bigger than height of the object, we say it is enlarged image, or sometimes we say magnified image, and the image will form beyond C. So we can say when the object is placed between C and F, that means center of curvature and focus, then the image that will be formed, it will be real, it will be inverted, it will be enlarged, and it will form beyond C. This is the sixth case when object is kept at focus. Now, any ray which is parallel to the principal axis, we know after reflection always passes to the focus. This ray also, after deflection from the mirror, it will reflect in such a way and it will pass through the focus. This is another ray which is in the direction of C. We know any ray in the direction of C, after deflection, retraces its path. That means it will move in the opposite direction. So from here, one ray will go, and after striking the mirror, it will reflect in such a way that it will pass through C. Here you can see the rays are almost parallel, and we know parallel rays meet at infinity. And for the formation of the real image, these rays are going to meet at infinite distance. So we don't know what is the exact location where image will be formed. When object is kept at focus, in case of a concave mirror, the image that will be formed, it will be real because rays are going to meet somewhere, and real images are always inverted, so it will be inverted image. It will be highly enlarged and it will be at infinite distance, or we can say the image will be at infinity. Now, if the object is kept between focus and the pole, then what will happen? This is the object. Any ray which is parallel to the principal axis, after deflection it passes through the focus. We know the rules. Another ray which is in the direction of C, it will retrace its path. That means it will move in the opposite direction and it will pass through C. As you can see, these two rays are diverging. They are not going to meet. This is one reflected ray. This is another reflected ray. If we produce these two reflected rays in the backward direction, we are going to get image. Since rays are not really meeting, they appear to come from this point. That means the image that will be formed, it is virtual. So, when object is kept between pole and the focus, image that will be formed, it will be a virtual image. It will be erect because virtual images are always erect. As you can see, when object is like this, and image is also in the same direction, then we say they are erect. And if object is this, image is this, then we say it is inverted. And here you can see the image is virtual, it is erect, it is magnified because height of the image is more than height of the object and the image will form behind the mirror. So these are the characteristics of the image formed by a concave mirror when the object is placed between focus and the pole. Now what are the uses of concave mirrors? It can be used as a shading mirror. Why? It is because when the face of a person is between pole and the focus, when the face of the person is between the pole and the focus of a concave mirror, an erect and magnified image is formed, and as a result shading becomes easier. That's why concave mirrors are often used as a shading mirror. It can be even used for makeup mirror. Concave mirrors are also used as reflectors in headlights in automobiles such as cars and trucks. Even the reflector of flashlight is concave in nature. The bulb is placed very close to the principal focus of the concave reflector when a powerful, almost near parallel beam of light is formed. It can be used by doctors to focus a parallel beam of light on a small area, especially for the examination of throat, ear, nose, teeth, etc. Even concave mirror can be used as a reflector in dish-type solar cookers and solar furnaces. So in this way many uses are there. For exam purpose, at least 3 uses you must know. Now let me discuss the rules for drawing images for convex mirror by ray diagrams. So rule number 1 is that any ray of light traveling parallel to the principal axis, this one is principal axis, so any ray of light traveling parallel to the principal axis of a convex mirror after reflection appears to diverge from the principal focus of the convex mirror. So here ray will come like this. After that, from this point it will reflect and it will diverge this way and it will appear as if it is coming from principal focus. That's why we have given dotted lines. Now rule number 2, any ray of light which travels along the direction of principal focus. In this case, this is the principal focus, this is the center of curvature, this is the pole. So any ray of light which travels along the direction of principal focus, just see it is in the direction of principal focus, after deflection will travel parallel to the principal axis of the mirror. So here this ray is approaching the mirror in the direction of principal focus. After striking the mirror at this point, it will reflect in such a way that reflected ray will become parallel to the principal axis. This is rule number 2. Rule number 3, any ray of light which travels along the center of curvature of a convex mirror after reflection retraces its path. That means the ray which is in the direction of C after reflection from the mirror will retrace its path. It will move in the opposite direction. This is rule number 3. It is because the ray is striking the surface of the mirror at right angles, and that's why it's a normal incidence and it reflects back in the opposite direction. And now rule number 4. According to the rule number 4, a ray of light incident obliquely on the principal axis towards the pole. Any ray of light incident obliquely on the principal axis towards the pole of a convex mirror is reflected obliquely such that the angle of incidence at P is equal to the angle of reflection at P. That means this angle and this angle, these two angles will be equal. So any ray of light which is striking the pole, it will reflect in such a way that the angle formed by the incident ray with the principal axis will be equal to the angle formed by the reflected ray with the principal axis. So these are the 4 rules of reflection of convex mirror. Now let me explain the formation of image in a convex mirror for different positions of the object. And in the first case, we have considered the object is at infinity. The rays coming from an object situated at infinity are always parallel. So these are the parallel rays, and here we have drawn these rays are parallel to the principal axis. When these rays strike the convex mirror, they will diverge outwards as if they are coming from focus. When this diverging reflected beam enters our eye, these rays appear to come from the point F. These rays appear to come from the point F, which is the principal focus. So, image of the object which is at infinity will form at principal focus. Since here the rays appear to meet, so image is virtual. Virtual images are always erect. Virtual images are always erect. And as you can see, a very small image will be formed, point size, so it will be highly diminished, and image will be at F, which is the principal focus, and it will be behind the convex mirror. So when object is at infinity, image will be at focus, it will be virtual, it will be erect, it will be highly diminished. Now in case 2, we are keeping the object between the pole of the mirror and infinity. You can place it anywhere. Always image formation will be of the similar type. Here as you can see, from this object, rays are going in different direction. Any ray which is parallel to the principal axis, after striking the mirror, it will diverge as if it is coming from the focus. Another ray which is in the direction of C will retrace its path. So this is one reflected ray, this is another reflected ray. These two reflected rays are not going to meet anywhere. So if we produce them in the backward direction, it appears to meet here. That means if this is the object, this will be the image. And here, since the rays appears to meet, the image is virtual, it is erect. The height of the image is smaller than the height of the object, so we can write it is diminished, and the image will form between P and F behind the convex mirror. So wherever you keep the object between infinity and pole, in all the cases we are going to get similar image. The image will be virtual, it will be erect, it will be diminished, and it will form between P and F behind the convex mirror. These two cases we have to consider for the formation of image in a convex mirror. Now, how to distinguish between a plane mirror, convex mirror and concave mirror without touching their surfaces? For this, what we have to do? Just keep the object very close to the mirror, and if the size of the image is same as size of the object, in that case it must be a plane mirror. If the size of the image is smaller than the size of the object, then the mirror is convex in nature. If the size of the image is bigger than that of the object, then the mirror is concave. So only by keeping the object very close to the mirror, we can distinguish between a plane mirror, convex mirror and a concave mirror. Now let me discuss the uses of convex mirrors. We know in case of a convex mirror, when object is between infinity and pole, the image is erect and diminished. So it is used as a rear view mirror in automobiles because it can cover a very wide field behind the driver and hence enables to see the traffic behind him without turning his head. A plane mirror is not useful as a rear view mirror because its field of view is small. This type of mirrors can be used as a reflector for street lights because it diverges rays over a large area and hence illuminates that area. Even convex mirror can be used for safe view of dangerous corners. So it has multiple uses. For the exam purpose, at least try to remember 3 uses of it. To specify the position of the object and the image, we need a reference point and sign convention. The sign convention that is followed nowadays is called new Cartesian sign convention. In maths you must have done Cartesian plane where this line is called x-axis and this is called y-axis, and the point where this x-axis and y-axis intersect, that point is called the origin. According to new Cartesian sign convention, the conventions are the object is always placed to the left of the mirror. Since this is the mirror, we have to keep the object in this side. In case of concave mirror also, we have to keep the object in the left hand side. Second point is that all distances parallel to the principal axis are measured from the pole of the mirror. So all the distances, if we want to measure the distance of the object, we have to measure from the pole of the mirror. And this principal axis of the mirror is taken as x-axis. We know in this x-axis, if this is the origin, in the right hand side it is positive, left hand side negative, in the upside it is positive, and here it is negative. Similarly here, the pole is taken as the origin. All distances in the right side, are taken as positive. Here you can see, suppose this is the image in certain case, so this distance will be taken as positive, and the distances in the left hand side, this distance will be taken as negative. Suppose this is the object and this is the image. Here object is perpendicular to the principal axis. So distances measured perpendicular and above principal axis are considered as positive, so this will be considered as positive and this height will be considered as negative. So according to new Cartesian sign convention, object always we have to keep in the left hand side. All distances we have to measure from the pole of the mirror. This principal axis is considered as the x-axis. All distances in the right of the principal axis is considered as positive and all the distances in the left of the principal axis are taken as negative. All the distances measured perpendicular and above principal axis are considered as positive and distances measured perpendicular and below the principal axis are considered as negative. So these are the modern sign conventions. Let me give one or two examples now. Now in this case, this is the object, this is the image. So PB is the object distance because all the distances we have to measure from the pole. So PB is the object distance and since it is in the left hand side, it will be considered as negative. So object distance PB is written as minus U. U is the symbol which is used for object distance. Here A1, B1 is the image and distance of the image from the pole is PB1. Now you can see PB1, this distance is in the right hand side, so it will be taken as positive. So image distance PB1, we write plus V. Image distances are represented by the symbol V. Here object is AB and height of the object is AB, which is above principal axis. Since it is above principal axis, this will be represented as plus HO, means height of the object, and A1, B1 is the height of the image. This is also above principal axis. Just because it is above principal axis, this will be plus HI. And here F is the focus and PF is the focal length. Since focal length is in the left hand side of pole, so focal length PF will be minus F. I hope this one is clear. Let me give you another example. In this case, this is the object. Object is kept between C and F. Here the ray which is parallel to the principal axis, after deflection, the ray passes to the focus. Another ray which passes to the focus, after deflection it will become parallel. So these two reflected rays are meeting here. So A1, B1 is the image of AB. Here AB is the object, A1, B1 is the image. Now since this is the pole and we know according to the sign convention we have to measure the distances from the pole of the mirror. So since AB is the object distance is PB, and since it is in the left hand side of pole, it will be negative. So object distance PB we have to write minus U. Here image is A1, B1 and now distance of the image from the pole is PB1. Since it is in the left hand side, image distance PB1 is minus V, where V is the symbol for image distance. Here AB is the object, so height of the object is AB and it is above principal axis. Since it is above principal axis, it will be plus HO, where HO is the height of the object, and A1, B1 is the image which is below principal axis. And we know according to the sign convention, the heights which are below principal axis are considered as negative. So height of the image A1, B1 is minus HI, where HI represents height of the image. And here focus is F, so PF is the focal length. Since PF is in the left hand side of pole, focal length PF is minus F. I hope the sign convention is now clear. Relationship between the distance of the object from its pole, that is U, the distance of the image from its pole, that is V, and the focal length F of a spherical mirror is given by the formula 1 by V plus 1 by U equal to 1 by F. And this formula is valid for all situations, for all spherical mirrors. This formula is commonly known as mirror formula. Again, whenever we compare the height of the object and height of the image, that ratio is called magnification. Now magnification produced by a spherical mirror gives the relative extent to which the image of an object is magnified with respect to the object size. Magnification is generally defined as the ratio of the height of the image to the height of the object. We know height of the image is represented as HI and height of the object is HO. So magnification is height of the image divided by height of the object. And since it is a ratio, so it will not have any unit. Magnification can also be written as minus image distance by object distance. So minus V by U. So we can write magnification equals to height of the image by height of the object or minus V by U. Now for a plane mirror, we consider magnification is +1. This 1 indicates that height of the image is same as height of the object, and this positive sign indicates that the image is erect. As erect images cannot be taken directly on the screen, therefore the image is virtual. And that's all for today. And that's the end of mirror section. In the next part, I am going to explain refraction of light. Till then, bye bye, take care, and wait for the next video.